Welcome to our first video on implicit differentiation. A curve or an equation is implicit if the x's and y's are all mixed up. So an easy example of this would be something like this, which is the equation of an ellipse. We're used to seeing an equation of ellipse where the x's and y's are all mixed together. Okay, now explicit functions are ones where you have, y equals stuff in x. Okay, so these are not equivalent. I just made up a second function. All right, so the idea here is that we want to be able to find the derivative of a function implicitly, meaning let's not rearrange it, let's just go for it. Okay, so what our goal is we want to find dy dx, because that will give us the slope of our curve. I say curve instead of function because an ellipse is not a function. So many of these things aren't functions. They're just curves, which we could graph in Desmos and see what it looked like. Okay, so we want to find the derivative with respect to x. So how implicit differentiation works is that you treat x normally, but if you have a y term, because y is not an x, you have to tag it or multiply it by dy dx. Okay, so what'll happen is we're going to get a bunch of terms in our answer, but our goal is we're going to solve it for dy dx. And my answer will have x's and y's usually. Okay. So we're going to go ahead and find the derivative of this ellipse and see how it goes, and then I'll have a couple more videos of crazier curves. Okay, so let me pause for a second while I erase. All right, we're back at it. So I'm going to take the derivative of this. Now, in my homework solutions and in my notes, you'll see me write this just because I don't want it to look like magic. I want you guys to know that I took a derivative. So here, when I take the derivative of x squared, because it's an x, I just take it normally, which is 2x. All right, coming to the next term. If this were an x, I would write 8x or 8y. But because it's a y and not an x, we are going to do the tagging of the dy dx. Okay, what it really is chain rule. It's saying take the derivative of the outside and then take derivative of the inside just being y. All right, the derivative of 16 is 0. All right, now our goal is to get dy dx alone. So we are going to move the 2x to the other side, and then we'll divide by 8y. And I can make that a little bit cuter. I could reduce it by 2, so it looks like the slope at any point on the ellipse is given by negative x over 4y. Okay, notice what I just said. So the ellipse, which we were originally given, if I had a point that lives on it, so for example, the point 4, 0 lives on it, then I would plug in x is 4 and y is 0. Now, some of you might be panicking like, Jen, plugging in 0 in the denominator is bad. I know, that would be a vertical tangent line in this instance, okay? I just said all that really fast, so let me actually show you what I'm saying. So x squared plus 4y squared equals 16. If you graph that in Desmos, what you'd get is 2 in the y, 4 in the x. So if I was talking about this point 4, 0, so think about this tangent line at 4, 0. Yep, it's vertical. It's a vertical tangent line. Vertical lines have undefined slope. So notice what happens when I plug in 4 and 0 into this equation. I get undefined slope. So it does in fact work. Okay, if I were to plug in this point here, which is 0, 2, think about a tangent line that's here. That tangent line would have a slope of 0. Let's see if that's true. Negative 0 over 4 times 2 is 8. Negative 0 over 8 is just 0. So yes, it is still holding true. Okay, so this formula for our derivative will still give us the slope of the curve or the slope of the tangent line at any particular point on this implicitly defined equation. Okay, we're going to do a couple more examples so that you can see how bad it gets. That's a good way to say it.